I'm not quite ready yet either. Got a couple exams to prepare, a lot of stuff to grade. What's that? Partly, so I'll talk about it in just a second, but about the scheme. But I'm gonna do a little bit of true false multiple choice like we have been doing, and I don't have that part yet, and I need to cut back some of the other part. But we'll talk about that in a moment. So here's the attendance. I wanted to remind everybody the exam time. Location will be here like normal. Exam will be on Wednesday. Okay, I'm recording that just in case we have some stream issues. Like I mentioned, we're going to do a partially cumulative exam. As I was thinking about it, in beginning to prepare the exam, I realized that I don't really want to do the multiple choice true or false as the cumulative. I'll keep that portion strictly on the recent stuff. So in terms of solving problems, it's a bit cumulative, about 50% cumulative. In terms of knowing a little bit more topical things about, let's say, wastewater regulation or that type of stuff, that part will be strictly on the wastewater BOD, so wastewater regulation, treatment goals, BOD testing, removal modeling, nutrient removal. Those topics will be the true-false multiple choice, 100%. And the remainder of the exam, which is probably 70 to 80% of the exam, will be 50%. So the free response problems, this is 50-50. And this part will be 100% not cumulative. So 0% cumulative. We'll say it that way. If that makes sense. I don't know if that's the right way to say it. A wastewater problem, because we also use sedimentation for wastewater. So maybe I would mix it up a little bit, but this is what you can expect in terms of topics, the breakdown, 25% from the first exam, 25% from the second exam. And you'll find the nature of the course, it is quite cumulative. You've been doing mass balances from day one, and they're still relevant, right? Okay, so that's what you can expect. And I don't have it quite finalized, but getting there. Any questions on that? All right. So we will get going with the homework solutions then. And as soon as we're done with that, if there are no other questions, we'll have you on your way. So problem one, we have a wastewater treatment plant using activated sludge for secondary treatment, and we're given a flow rate of 0.35 cubic meters per second, primary effluent. So it might be good to go ahead and draw that up. Primary effluent would be what's leaving the first clarifier, the primary sedimentation, going into our activated sludge basin. Normally this will go into a second clarifier, and we might have recycle. But I'm going to just leave it right there for a moment and say that we have this flow rate should be the flow rate leaving this guy, right? This guy has some flow rate leaving, maybe an effluent from the primary. That guy is the 0.35 cubic meters per second. Okay, then we have the mixed liquor suspended solids concentration is 2,500 milligrams per liter VSS. That is going to be the X concentration within the reactor. It's going to be the mass concentration of bacteria in there. Then we have an RAS concentration. That would be our return activated sludge. That means we do have recycle. The XR here, go ahead and label that. So the X was 2,500 milligrams per liter VSS. Okay, then we have the substrate concentration. Again, this is mentioning the primary effluent. So keep track, and this is what I like to do with drawing it, is keep track of what pieces are going where so we understand what we're talking about. So primary effluent, this is the primary treatment. The effluent to that is what's leaving it. So we have an S here, we'll call it S naught. That is 220 milligrams BOD per liter. Then we have our given F/M ratio, the food to mass ratio. As I've told you in the past, we keep this as one unit, not food over mass. It is a ratio, a daily ratio of how much food they have, and we're going to keep that set as one parameter. 0.52 milligrams BOD per milligram VSS per day. And then we have a cell retention time, we call that theta C, of 9 days. Okay, so that's our problem set up. Before I even looked at what it was asking for, I wanted to make sure I was clear on what pieces are where and that I can picture everything in my mind. So part A says, what is the volume of the activated sludge tank? So now that we have all that, we ask ourselves, well, what is that volume? And perhaps, what would we do to find it? A lot of times we'll use theta, right? Theta is V over Q, but we don't know theta. And so instead, maybe we should look to theta C. We are given theta C. Can we get volume from that? We know that's 9 days. Well, if we take a look at our equation, we have an equation for theta C. It's the retention time on average of solids, which we defined as kind of multiplying the V over Q by X, but the Q is a little more complicated because we have a recycle that's important. So this becomes, as we have in the formula sheet, Vx over QW XW. Okay, so now we have a little bit more information that we can use to find this value. What I didn't leave room for myself to show here is in our drawing we can show we have QW leaving here with XW. XW should be equal to XR. And then there's a question about, well, what is our QW? Maybe we have something else that can find us that value. With this equation, maybe we could rearrange it. But let's take a look at what else we have before we get too much further. So this is one way we can get at V, but we don't know QW. And maybe we'll need to find that. So looking at our other equations, we can also take a look at the fact that we have an equation for the F to M ratio. This one was Q S naught over Vx. And if we look at the parameters here, we have everything except for V. So this is probably the one we ought to use. So we can't use that because we don't know V, or we don't have it, we don't know a theta rather. We can't use this one because we don't know the QW yet. But this one we know Q, we know S naught, and we know X, and we know F/M. So rearranging, yeah.
So for the F to M ratio, the Q that you're using is not the combined Q that's going into the reactor, it's primary F.
Correct. And the reason for that is because the Q that is bringing S naught, because we're using S naught, we are not changing the influent here. The amount of substrate coming in would change with that recycle line, or we could draw our control boundary further out and say whatever is coming into the system in total, new stuff coming into the system, is our Q that is the effluent from the primary times the substrate that's the effluent from the primary. That is the new substrate coming in. Everything else is just recycling in there, or just being taken care of. So this Q times S naught is important because it's giving us a way to look at the exact amount coming in. That's the daily amount coming in. That'll be the volume per time multiplied by the amount per volume. Okay, so then all we have to do to solve this is rearrange V equals Q S naught divided by S/M times x. We have each of those parameters. So we'll say, do that. And this should come out to be 5,118 cubic meters, which is quite large, probably larger than any realistic system. But for the parameters given, that would be the answer.
Will you convert the Q into meters cubed per day?
Yes. And I'm not sure if actually I did. I had that written on my notes, so I didn't find the answer, but we would say Q was 0.35 cubic meters per second. Of course, we have to count exactly like you said to convert it to days. So that would be 86,400 seconds in a day. Okay, so part B asks what is the waste activated sludge flow rate? So how much are we wasting per time? Here's where we need our QW. And if we flip back a second, we kind of wrote down all the possible equations we might want to use. And theta C would make use of that, but we needed volume, right? We didn't know QW, but now we can solve it because we have the volume. So we can rewrite that equation. Theta C is Vx over QW XW. We recognize that we can simply swap the QW with the theta C. And again, we need the theta is in days, so that QW will be in days. When we put in the numbers here, this should become that 5,118 cubic meters, times the X, which was given at 2,500 milligrams VSS per liter. All this divided by the 9 days times our XW is equal to the XR. That was also given at 10,000 milligrams VSS per liter. Okay, putting all that in, this should give us a theta C of, a QW. We'll just say of 142.2 cubic meters per day. Okay, so pretty straightforward there, as long as we have our units set up correctly. Part C asks, what is the flow rate of the secondary treated effluent? So again, we might want to be looking at our overall system design in all of this, where we have our reactor, our recycle, the QW is here, and we could say this is the Q effluent. And here, all we need to do is a balance on the Q, because we have Q effluent from the primary coming in. That was given. And then we could say, if we draw a control boundary like this, all we need to do is say what's going in versus what's going out, right? Exclude all of the recycle stuff. We don't need to account for it because it's all within that picture. We just need to look at what's crossing the boundaries of that larger control volume. So that means Q that was given is going to be equal to QE plus QW, or QE will simply be that initial Q minus QW. And we do that, we'll put this QW in cubic meters per second. This comes out to be 0.00165 if we convert that to seconds, cubic meters per second. So QE would be 0.35 minus that. Or QE will be 0.348 cubic meters per second. Of course, you could potentially report that in per days, and that would be fine also. All right, make sense? Part D asks, what is the hydraulic residence time? This will simply be V over Q now that we have the volume and we know the flow rate. But again, the important thing is to take a look at our control volume. We make an important assumption in this type of problem that none of the volume of our clarifier matters for the reaction. So we're not bubbling air through it. The water's not staying there for a terribly long time. And so we make an assumption that the volume there doesn't matter, doesn't add to our system, and therefore we can draw our control boundary beyond it and ignore the recycling flow rate. So the total flow that's going through the reactor that does biological treatment is the Q. Is the Q that's coming across this control boundary. Okay? So that's going to be our Q, and the only volume that's important is going to be the volume in that tank. So this would then just be the 5,118 cubic meters divided by our 0.35 cubic meters per second. That's 14,000 seconds and some more, or 0.169 days. Good on that. All right, problem 2. We have some incoming wastewater with a BOD equal to 200 milligrams per liter. It's treated in a well-run secondary treatment plant that removes 90% of the BOD. You are tasked to run a 5-day BOD test with a standard 300 milliliter bottle using a mixture of treated sewage and dilution water, no seed, because not needed. And we're going to assume the initial DO is 9.2 milligrams per liter. So part A says, roughly what maximum volume of treated wastewater should be put in the bottle if you want to have at least 2 milligrams per liter of dissolved oxygen at the end of the test? You're filling the rest of the bottle with the water. You're filling it completely, and you need some amount of wastewater in it, right? So what's the maximum volume of treated wastewater that you would put in it? Now the trick here, or the thing to note here, is treated is highlighted. So it has already passed through the treatment, and we know something about that treatment, right? It removes 90% of the wastewater, of the BOD, excuse me. So we have 200 milliliters. So the initial is 200 milligrams per liter of BOD. That means the S and the effluent, or the treated, should be 10% of that, right? So this should be 20 milligrams per liter of BOD. That means what we're putting in our bottle is 20. So when we set up our BOD equation, we would say that is 20 milligrams per liter. And we can say that's going to be equal to the dissolved oxygen initial minus the final divided by the dilution coefficient. And the dilution coefficient is where we're going to find the answer, right? Because that is the volume of the wastewater divided by the total, which is 300 milliliters. Okay, so that's our problem set up. Now we just need to put in the different pieces and solve for that volume of the wastewater. In fact, I'm going to go ahead and multiply both sides by the P here. So we get volume of the wastewater that we want to solve for divided by 300 milliliters. I'll go ahead and leave the 20 milligrams per liter here for a moment. And that's going to be equal to the dissolved oxygen initial, which was given 9.2 milligrams per liter, minus the final amount that we needed, which was 2 milligrams per liter at the minimum. think, right? Yeah. So now we have our system. All we have to do is take that on the right side, that'll become 7.2. Divide that by 20, multiply it by 30. We should end up with units that give us, because these are units of milligrams of oxygen, and biological oxygen demand will account, those units will account for that. So we have 7.2 divided by 20, and then multiply that by 300 milliliters, and we'll get our answer. Should give us 108. So this will yield us a volume of the wastewater of 108 milliliters. All right. Does that make sense? Okay. Part B says if we make the mixture half water and half treated wastewater, what DO would you expect after 5 days? So the question really is, we know it reaches 2 milligrams per liter if we did a third of it as wastewater, approximately, maybe just over a third. So the question really is, do we even have any oxygen left? So that's kind of the setup, and we can test, or calculate rather, what should it be if we left it with half and half. So P would be 1 over 2, and we can set it up accordingly. So this is the 150 over 300. And we can set up our system to say, well, our BOD5 is 20 milligrams per liter. And we know that's going to be some dissolved oxygen initial concentration. We're going to solve for the DO final divided by 1/2. So we can see that it should be 40. If we multiply both sides by 2, that'll get rid of the 1/2 on the bottom, equals 9.2 minus dissolved DO final. If I've done that correct. Oh, excuse me, I did that backwards, 10. Multiply both sides by 1/2. Okay, with that, we should find that our DO final would be a negative number, right? Negative 0.8 milligrams per liter. That's not possible. So we're going to say the closest possible thing that could exist would be 0, right? It would deprive the whole thing of oxygen. All right. Make sense? Okay, moving along. So problem 3, we have a BOD test that's run using 100 milliliters of treated wastewater mixed with 200 milliliters of pure water. The initial dissolved oxygen of the mix is 9 milligrams per liter. After 5 days, the dissolved oxygen is 3 milligrams per liter. And after a long period of time, the DO is found all the way down to 2 milligrams per liter. So what we know already is we have a 5-day BOD test and then a very long BOD test. So we're given some information about a longer period of time where BOD is processed. And it no longer seems to be dropping. So that essentially gives us the ultimate BOD, the amount that will be consumed if we give it as long as it could ever want. Assume nitrification has been inhibited, so only BOD measured is carbonaceous. Okay, so what is the 5-day BOD of the wastewater? That kind of brings us back to the same type of thing we were just doing. Very simply, we have BOD 5, DO initial minus DO final, divided by the dilution factor. This is simply going to be the 9 minus 3, and we were given 100 out of 300, so this will be 1/3 here. So 9 minus 3 is 6, times 3 would be 18. This is going to give us 18 milligrams BOD 5 per liter. All right. So part B says, assuming none of that nitrification stuff, estimate the ultimate carbonaceous BOD. So the ultimate, that is our L naught, or it's also called the BOD at an infinite amount of time, or at least a sufficient amount of time where it's no longer any oxygen demand. Right, so maybe that's 20 days or 2 months or something, but it's enough time where the oxygen is no longer changing from these processes. So we can say that would simply be same process here, DO initial minus the DO final divided by the 1/3. This is going to give us 9 minus 2 is 7 times 3 should be 21 milligrams BOD per liter. So DO initial was still 9, and this one was measured at 2 after a long time. Okay, does that make sense? All right, so this is how we're connecting the BOD tests to this modeling stuff, because you'll recall that this parameter began to be important in terms of understanding if we discharge something downstream, what's going to happen. That's where we got the fancier formulas involved. So that's where we're going with part C and so on. C says, what would be the remaining BOD after 5 days had elapsed? Well, this one's a little simpler. So the amount remaining at some time t, we call this LT. This would simply be the ultimate amount minus the amount that has already been demanded. So this is going to be 21 minus 18. Because we just solved these two numbers, right? So after 5 days has elapsed, we have 3 milligrams per liter of BOD remaining. Then part D says we want to estimate the reaction rate constant, K, per day. So this is referring to the reaction rate of BOD removal from the system. So this will be, if we model the BOD removal, BOD at some time t, we can describe it as L naught times 1 minus e to the negative kt. And we need to find that k. And if you remember, we mentioned in class, this is similar to the deoxygenation rate constant, but not always exactly. So we're just going to call this the BOD reaction rate constant. So we actually know the T. If we set that at 5 days, we know something about the BOD at time t, and we need to know something about L naught we were given, and then we can put the pieces together and solve the problem. So we know L naught was 21 milligrams BOD per liter. We know the time, we know a time that we can work with is 5 days. So we can say the BOD remaining at time 5 days, that's going to be our the value that we just solved previously. So I'm going to rearrange this just a little bit and say e to the negative kt will be equal to 1 minus the BOD at time t divided by L naught. And then we can take the natural log of both sides, so we get negative kt equals the natural log of that. 1 minus BOD at time t divided by L naught. When we put these pieces in, solve for k, we should get k equals 0.389 per day. Right, does that make sense? So problem 4, this one's from our book, says suppose the only source of BOD in a river is untreated wastes that are being discharged from a food processing plant. The resulting oxygen sag curve has a minimum value of dissolved oxygen somewhere downstream equal to 3 milligrams per liter. So if we take a look, oxygen dips all the way down and reaches 3 milligrams per liter somewhere downstream. Just below the discharge point, the DO of the stream is equal to the saturation value of 10 milligrams per liter. Part A says, by what percent should the BOD of the wastes be reduced to assure a healthy stream of at least 5 milligrams per liter of dissolved oxygen everywhere? And then the question adds to that, would a primary treatment plant be sufficient to achieve this reduction? So we want to essentially move this minimum up to a value of 5. So if 5 is kind of the halfway mark, we need it to somewhere around there. And a new sag curve would look something like that. The question is a primary treatment plant sufficient? And we could take a look. Primary treatment plants might remove 10 to 20% of BOD. They're not super effective, but it's certainly something. And maybe I should look that up, or maybe you can Google that for me to get what AI thinks it is, or finds that it is. But I think it's something like that. So we'll keep that in mind, unless you correct me. What I should do is go back and look at the book and remind myself what the book says about it. All right. Anyhow, the secondary treatment is what we usually use to remove the bulk of it. So that'll be more like 90 to 95%. So coming back to the primary part of the question, however, what does it take to go from 3 to 5? So we need to know a few things. One, we probably need to know, where does this DO minimum occur? So where in time and in location is that X critical? That will correspond to some critical time, and then we can evaluate from there. Although that would be what we need to, in order to solve. Sorry, I was looking at my notes. We might need that for our time in our equations, but actually, if we look at those equations for a moment, because this would give us the time critical, right? But I think we don't need that just yet. Because if we look at our equation, the deficit, and this is what we want to go from a deficit of 7 to a deficit of 5. This has a function, and by the way, we're also given a few parameters here. This function looks like KD L naught divided by KR minus KD. A quick check looks like KR is not equal to KD, so we're fine to use this one. All this multiplied by e to the minus KD t. So that t tells us maybe we need that, but we're going to hold that thought for just a moment. So e to the minus KRT plus dissolved oxygen initial, or the deficit initial, excuse me, which is 0, but we would say that's to the negative KRT. So because we have no initial deficit, that term goes to 0. So we have this equation. Our deficit is equal to some ratios times e to the minus kdt minus e to the minus krt. Now, what we'll recognize is the deficit here is proportional to the initial amount of wastewater, or excuse me, the initial amount of L naught, the ultimate BOD. So it is proportional there, and if time is constant, everything else is a constant. in this equation. So we have no reason to think that the time that this would occur would change. Our critical point is just going to end up at the same critical point regardless. We'll see that in a few minutes. So we can actually solve this without knowing the time, because we can say that essentially the d at the deficit of 5 divided by the deficit at 7 is going to be equal to the L naught with the 5 deficit divided by the L naught with the 7 deficit. So that's going to be quite convenient, and we can then solve. We can say, well, we need the deficit of the ultimate BOD that corresponds to the 5 milligrams per liter deficit. That ratio here is literally 5/7. So the new L naught to achieve our new deficit value is simply going to be 5/7 of the original L naught, is what that's saying. And that will, because everything else in the problem is constant, that will be proportional. Okay, so that part, we end up at a simpler situation. As a fraction, this would be 0.714 or 71.4%. Okay, we have a question. Does the initial deficit cancel because it is assumed to be at the saturation, like the right before the discharge? Yeah, the portion on the right, the initial deficit, the right-hand part of the equation, goes away because it's multiplying by a 0, because there is 0 deficit when we start off. Now, if you're referring to the L naught here, we are actually just relating the deficit to the L naught. But I think the first part was your question. All right. So we have this, okay, great. We have this 71.4% removal, or excuse me, that's remaining. That's the value that would be remaining in the water that achieves the 5 milligram per liter DO deficit instead of the 7 milligram per liter deficit. So then, in terms of removal, we could take 1 minus that and get 0.286 or 28.6% removal is needed. So I guess it depends a little bit on how efficient the primary treatment is, how much BOD it's going to remove. My guess is it would not be enough. So the primary treatment enough, it might be close. Anybody look at a typical number up for me? No? Okay. Well, let me know if you do. Any questions on that? Does that make sense? Okay, so this one is a little odd because it's you could move forward and find the time and then come back here and put it in. What you'll find is even if you solve the time for 2 different deficits, it's the same time. You'll get the same parameter with the next equation, which we get to in part B. So I'll highlight that in just a second. But ultimately, you could solve it moving ahead, solving the time, and then coming back and putting the time in there for a calculation with one deficit, and then compare that with the other deficit. It'll all fall out and simplify just like this. Okay, and it would not be a problem if you did do that. It's just a matter of, the way the problem is structured kind of shows you maybe you don't have to go that far just yet. So problem B says if the stream flows 60 miles per day, that's our velocity, we're going to call that U. And the reaeration, that should be, has a reaeration coefficient. Kr equal to 0.8 per day, and a deoxygenation coefficient of Kd, 0.2 per day. How far downstream in miles would the lowest DO occur? Okay, so here we again are wanting to find XC that'll give us a time critical, which we could have used in the previous problem, as I mentioned. So we have an equation for this to find TC, which will, I guess we can go either way, right? We can go backwards because XC, the distance would be the velocity times time, right? U times TC. Our equation for TC is 1 over Kr minus Kd times the natural log of Kr over Kd times 1 minus the initial deficit, which is 0, so this is going to cancel. So this whole thing will become a bit simpler, but Kr minus Kd divided by Kd times L naught. So what you'll notice here is when we have no initial deficit, the L naught does not matter in the time equation. If we did have some initial deficit, then this might matter, and my approach in the part A would not work. So maybe we ought to have looked to this equation before coming to that conclusion. But given this entire part of the equation, we can ignore, right? So then our time is only going to depend on Kr and Kd, just those. When we solve for that, we should get a time value of 2.31 days. And that will, if we multiply that by 60 miles per day, that'll give us 138.6 miles. Okay, and that's the answer for how far downstream. Okay, does that make sense? All right, part C says, what is the ultimate BOD, L naught, of the mixture of the river and waste just downstream of the discharge point that would cause a minimum DO of 5 milligrams per liter? So that's kind of coming back to the initial portion. We now want to calculate that value. So if our deficit that we're going to find is 5 milligrams per liter, we can simply use that deficit equation and set that equal to this equation and solve for L naught. So this would be Kd times L naught. We're going to solve for L naught here. Divide by Kr minus Kd times e to the minus Kdt minus e to the negative Krt. All of that plus the initial deficit times e to the minus Krt. Again, that guy going to 0. So if we rearrange and solve, put in the numbers and solve for L naught, it's just a little bit of algebra and calculator work. We should get an L naught of 31.75 milligrams BOD per liter. Okay, so the wastewater treatment plant, then, if we're only going to do, if we think about it, how much damage are we doing to the ecosystem? How much oxygen are we depriving the ecosystem from? If we are okay taking away half of the oxygen at the worst scenario, so going from 10 down to 5, then we can actually discharge 31, almost 32 milligrams BOD per liter. So if you left that in a jar, it's going to completely deprive it of oxygen, and that would be bad. But given that the stream has some mixing and everything, we see that it has some capacity to take some waste. Any questions there? Right, so part D, last little bit, says sketch the oxygen sag curve before and after the treatment recommended in part A, labeling critical points, DO minimum, and the location and value. So we kind of already did this a little bit on our plot, the initial graph, but we'll go ahead and do it again. If this is our dissolved oxygen on the x-axis, this is 10 milligrams per liter, 5, and 0. We'll note that we also have 3 labeled here. We have some time critical. This was the 2.31 days. Oops. Apologies. So also, we could put on the x-axis if we wanted to distance. That came out to be 138.6 miles. So if you think about that, that's pretty far downstream, right? That's quite a ways. All right, and up here, this is our oxygen saturation value. And so we could draw one curve. Let's do this. One curve that reaches down to 5. Comes back up. And the other, the dirtier water, will color this here. Comes down and reaches about 3. Before coming back up. Okay, not my best drawing, but you get the picture. All right, so that would be the homework. Any questions? All right, well, that's all I've got for you. So unless you've got any other questions for the exam, good luck on your finals. See you on Wednesday. And don't forget to fill out your surveys. I really do. I read every comment every year. I appreciate them. Even if you have something negative to say, I like that because I can help improve it for next time. If there is a way I can give you credit specifically, I don't know if they've changed it. They used to give a way for me to give you some extra credit specifically or whatever. I'll give you a point or two of extra credit on an exam or something. If I can assign it directly, I don't remember if they made that change. But please do it regardless. I appreciate it. I like the nice comments. I also like the negative comments. Just let me know how you feel. And I'll see you next week.